Welcome back to The Explainer. Today, we're going even deeper into how your computer's processor finds information. We're moving past the basics and into the really clever tricks that make modern computing possible.
Okay, so last time we laid the groundwork for how a CPU finds data. But, modern programming is all about complex stuff like pointers and arrays. So the big question for today is, how in the world does the CPU handle those?
So this is really the heart of the matter. When your code says, give me my array 5, you're not telling the CPU to go to memory address 1234. You're giving it a relative command. So how does it translate that into a physical location in RAM? Let's unpack the logic, because it's pretty cool.
Well, the secret lies in this really powerful concept called indirection. The best way to think about it is like a treasure hunt. Instead of a map that leads directly to the treasure, you get a clue that tells you where to find the actual map. It's a two-step process.
So with indirect addressing, the instruction itself doesn't have the final answer. What it holds is a pointer. And a pointer is really just an address that, you guessed it, points to another address. It's like someone telling you, go to that house over there. Inside, you'll find a note that tells you where the party really is.
It's this fundamental two-step dance. First, the CPU goes to memory to grab the pointer. Then, it uses the address it found there to go to memory a second time to get the final piece of data, the operand we're actually after. And that extra step, that's what gives the whole system so much power and flexibility.
And this visual lays it all out perfectly. You can see the instruction doesn't point directly to the data. Nope. It guides the CPU to an intermediate spot in memory, which then acts like a signpost, pointing it to the final destination. This quote just nails it. This core idea of indirection is what makes so much of modern programming tick, from the pointers you'd use in C all the way to how object references work in languages like Java or Python.
Okay, so now let's see how this idea of indirection gets taken to the next level. We're about to look at what is, arguably, the single most important addressing mode for dealing with complex data like arrays and objects.
So, take a look at this. This is a super common line of code. We're asking for the element at index 2 of an array. The question is, how does the CPU instantly find that specific piece of data without having to read the whole array from the start?
The magic here is a method called displacement addressing, and honestly, it's a beautifully simple idea, base plus offset. The CPU knows the starting point, the base address of the array, which it keeps in a super fast spot on the chip called a register. Then it just adds a calculated distance, the offset, to jump right to the data it needs.
So let's break down how r-char2 gets translated. The compiler sees this and goes, okay, I know where r starts. It sticks that address into a base register. We'll call it rbase. Then it calculates the offset. We want index 2, right? And each integer takes up 4 bytes. So 2 times 4 is 8. The final instruction for the CPU looks like this. Start at the address in rbase, jump forward 8 bytes, and load whatever you find there into register R1. And boom, just like that, it's got the number 30. And this base plus offset trick, it is everywhere. It's not just for arrays. Need to find a specific field inside a larger data structure? That's base plus offset. Need to grab a local variable off the program's call stack? You guessed it, same exact principle. This is the absolute workhorse of data access in computing today. All right, so we've got our heavy lifter. Now let's look at a couple of specialized tools in the CPU's toolkit. These are highly optimized for two very specific but incredibly important jobs: managing all the data for function calls and efficiently controlling where the program goes next. And what we have here are two really clever shortcuts. On one side, you've got stack addressing. When your code pushes data onto the stack, you don't have to give it an address. The CPU just knows, implicitly, to use the stack pointer, a special register that's always pointing to the top of the stack. It's automatic and incredibly fast. On the other side, you've got PC relative addressing. This is for jumps in your program. Instead of calculating a full absolute memory address to jump to, the CPU just figures out an offset from the program counter, the register that's tracking the very next instruction. It's like saying, just jump forward 10 instructions from where we are right now. Way more efficient.
Okay, so let's zoom out for a second. We've just armed our CPU with an amazing toolkit of addressing modes. It now knows how to find any piece of data, no matter where it is, whether it's a simple variable, an element buried deep inside an array, or a temporary value on the function call stack.
So just to put a bow on it, these are the essential tools that make our high-level programming languages actually work. Indirect addressing gives us the power of pointers. Displacement addressing is the engine for arrays and objects. And those specialized stack and PC relative modes, they give us fast function calls and efficient program flow.
So we've totally nailed the where question. Our CPU has a full set of tools for finding any piece of data it needs. But here's the thing, finding the data is only half the battle, right? Once you find it, you still have to actually do something with it. And that brings up a whole new question. How do you make that part go faster?
And that is exactly where we're headed next time. We are going to dive into instruction pipelining, the brilliant architectural technique that lets a CPU work on multiple instructions all at the same time, and it completely revolutionized processor speed. You are not going to want to miss this.